Hi, welcome to my talk. Today I will be giving an overview regarding our work investigating the semantics of futures in transactional memory systems. This is joint work with Shadi Issa, Paulo Romano, Luis Rodriguez, and Saif Halidi. I will start by introducing the motivation for this work, as well as some background materials. I'll then talk about the main contribution of our work, the semantics of transactional future, and an example implementation of the proposed semantic. Finally, I'll summarize what remains to be done. The observation that the same dollar buys twice the computation power every 18 months is no longer true. Sequential programs do not scale for free anymore. Industry's response was to introduce multi-core systems. The multi-core architecture is based on CPU's shared memory. Hence, program developers are driven to write parallel programs chasing performance improvement. However, despite many years' experience with parallel computers, multi-threaded applications are still difficult to write due to lots of coordinations and data exchange between threads. For that reason, we want to use abstraction to simplify parallel programming. Future is a popular abstraction for parallel programming. The future abstraction was first introduced by multi-Lisp language to express concurrency and use lazy evaluation. Let's have a very brief regarding how the future works. Thread A submits a future construct and gets a future object's reference in return. And then thread A immediately continues to execute some other computations without waiting for the future's execution to complete. And at the meantime, thread B concurrently starts the execution of the future expression. Thread A could evaluate the future's result whenever it needs. In absence of set effect, futures serves as an intuitive method to annotate potential concurrent code blocks. But what happens if they share states? Let's see an example. Thread A first initiates variable x and y to 1, and then submit a future task, which is executed by thread B. Note that the future abstraction is now create a computation, which reads variable x and y and returns the sum of them. The main thread A immediately continues while the other thread B is executing in parallel with the future task. Thread A sets the variable x and y to 10. Finally, after evaluating the result of the future task, thread A writes to a variable t the sum of z and x. As there is no coordination from the future abstraction between these parallel operations, the final value of z without synchronization could be 11 in the case that x reads the initial value 1 and y on the other hand observed the updated value 10. The resulting value of z being 11 is an anomaly which is not possible to be produced in any sequential execution. We see a typical two-thread sharing states example here. Future was meant to do asynchronous computation without set effect. Now we have a situation where the concurrent computations mutate shared states. This problem motivated us to introduce a mechanism to regulate concurrent access between tasks executed by the future and its spawning thread. Many synchronization mechanisms exist, and among them, transactional memory is regarded as an attractive paradigm to simplify the development of concurrent applications. Transactional memory borrows the abstraction of the atomic transaction from the database literature and applies it as a first-class abstraction in the context of generic parallel programs. By requiring programs only to identify which code blocks should be executed atomically and not how atomicity should be achieved. Roughly speaking, the transactional memory abstraction guarantees that the concurrent execution of a set of transactions can be explained via some equivalent sequential execution of them from an outside observer's view. I'll refer to transactional memory as TM for short in the following talk. Given the future's ability to generate parallel computations with complex dependencies, it is far from trivial to define intuitive yet precise semantics for what concerns isolation and atomicity. In the context of TM, this work was never done. As such, one of the main questions we wanted to address is how to use TM to regulate concurrent access when using the future abstraction. This question decomposes into theoretical and practical parts. Theoretical parts is formalizing which semantics should be enforced by a TM system that allows expressing inter-transaction parallelism via the future abstraction. The practical aspect is to assess whether the proposed abstraction can be implemented efficiently in a real TM system. We pursue the question by introducing a novel abstraction called transactional futures. In the process of searching for semantic models to combine future and transactional memory, several issues arise. I'll talk about them, how we reason about them shortly. The result of reasoning yields semantics describing the allowed behaviors with regard to atomicity and isolation. In our work, a formalization of the semantic is also provided. What is transactional future really? Transactional future are transactions whose execution is wrapped within futures, and they are spawned and evaluated by other transactions or transactional futures. As a result, we take advantage of transactional memory to regulate concurrent access to shared memory. In the meantime, within transactions boundaries, programmers are able to use futures to coordinate asynchronous computations. Ultimately, we study how to combine the notion of futures and transactional memory by encapsulating futures within transactions and allow them to be submitted and evaluated by other transactions or transactional futures. Since futures are able to generate parallel computations with complex dependencies, there exist several alternatives for defining the isolation and atomicity semantics of transactional futures, as well as their admissible serialization orders. Consider the basic example of similar read and write operations from the previous slide, but in the context of a top-level transaction, submit a transactional future. In another word, a future runs a transaction, and the transaction ends with a commit or abort. As in non-transactional futures, evaluate is used to retrieve any result produced by the future. Note the task executed by the future submitter up to the point where the future is needed is called the future's continuation. Given the simplicity of this scenario, it is straightforward to determine that the set of operations included by the transactional future and the continuation should be executed atomically. It is also intuitive to define their admissible serialization orders. All operations of transactional future should be serialized either before or after the operations of the continuation. Think of that we consider two different semantics regarding the plausible serialization orders of transactional futures and their continuations, namely strongly and weakly ordered transactional future. In either semantic, a future and its continuation should appear as executed atomically. With strongly ordered transactional future, the future should be serialized before its continuation, whereas with weakly ordered transactional future indicates that the future should be serialized either before or after its continuation. The name weak indicates this semantic is more relaxed than the strong counterpart, allowing more execution schedules to be accepted. With strongly ordered semantics, the serialization order of a future is defined prior to the future's activation. The strong semantic ensures that execution, a transactional future yields an equivalent execution in an otherwise sequential version of the program not using future. Weakly ordered semantics, conversely, requires programmers to determine whether application's correctness is still preserved independently of the order in which the transactional futures and their continuations are serialized. On the other hand, the ability of weakly ordered semantics to establish different serialization points for a future brings two benefits. The first is abort rate reduction. Imagine a continuation misses to observe the updates produced by the transactional future. In the case of strongly semantics, the continuation has to be aborted in order to read the updated value again. But this continuation can be spared from aborting in the case of weakly ordered semantics, because the future can choose to be serialized upon evaluation. The second advantage is struggler avoidance. Let's look at this illustrating example. Transaction T submits a transactional futures TF1, 2, and 3, one by one. Assume for resource constraints, there are at most 3 transactional futures can be running in parallel. TF1 here happens to be a straggler, which takes a relatively long time to execute. In the case of strongly ordered futures, although TF2 and TF3 finishes their execution, they are blocked waiting for TF1 to commit first, and then the following set of transactional futures 4, 5, and 6 can be submitted. In the case of weakly ordered semantics, TF2 and 3 can commit first, not waiting for TF1, as TF1 can choose to be serialized upon evaluation once it finishes its long executing operations, thus mitigate the straggler effect. The choice of strongly or weakly ordered semantics has also implications regarding the upper bound of execution interval of the commit operation. For strongly ordered transactional future, a transaction's commit request has to wait for all the futures bound by T have committed first. And for weakly ordered transactional future, the future's commit request may have to be blocked until the future is actually evaluated by someone else. There is another interesting yet challenging scenario where a future may escape the transactional context in which they were activated. This is an example of escaping transactional future, used as a complementary communication means by two different top-level threads. In this case, the top-level transaction T1 submits a transactional future TF. In TF's continuation, T1 writes the reference of the future to variable x, reads y, and commit. And the reference of TF is accessible to the other top-level transaction T2. This example highlights that the definition of continuation for escaping transactional future is very subtle, comparable to the definition of atomic continuation in the basic example in the previous slide. We use globally atomic continuation to consider all operations included in a chain of causally related events that leads to the evaluation. However, escaping futures can be evaluated after a long period, and it may be undesirable that they are not allowed to commit for such a long time. This led us to introduce an alternative semantic to ensure that an escaping future is serialized within its spawner. With locally atomic continuation semantic, any top-level transaction during its commit phase is requested to implicitly evaluate any escaping future is spawned. This evaluation is implicit since it is not requested explicitly by the programmers but is rather imposed by the considered atomicity semantic. Let's discuss the trade-offs of choosing different atomicity semantics. Globally atomic continuation allows the spawning transaction to commit without having to block waiting for escaping futures to commit first. On the other hand, this can have implications both on the efficiency of the TM implementations, which will have to maintain resources, for example, logs held by the futures. In addition, as the escaping futures execution interval is stretched, it becomes more likely to conflict with concurrent executions. And for the locally atomic continuation semantic, it avoid the commit interval of escaping future to be stretched. But on the other hand, a transaction is forced to wait for any transactional futures to complete before being able to commit. Finally, if we think of the relations between the proposed semantics, we note that if we choose the strong order semantics, this will render the distinction between globally and locally atomic continuation irrelevant. It is because a future serialization point is known in advance and is not affected by the set of operations included in its continuation. Now that we have analyzed and reasoned about the atomicity and the serialization orders between transactional futures and their continuations, how do we formalize these concepts? We have introduced a graph-based characterization called future serialization graph. This formalization is similar in spirit to the classic transaction serialization graph and aims to rigorously define transactional futures and their continuations, and moreover to capture the ordering relations between them. Future serialization graph is defined as a directed graph having the following set of vertices. A vertex VT begin represents the beginning of a transaction. VTC begin indicates the beginning of a continuation, and VT eval means the evaluation of a future. Besides the vertices, the following edges are defined as well. The first type of edge captures the sequential order of execution of the operations issued by a single thread. The second type of edge is from the future spawning vertex to the futures vertex. This edge indicates that a future cannot be serialized before its submission. The third type of edge goes from the futures vertex to its evaluation vertex, and it implies that a future cannot be serialized after its evaluation. Up to now, this future serialization graph enforces no ordering semantics. Next, we extend the graph with additional edges to reflect the ordering semantics. Recall that strongly ordered semantics requires a future to logically be serialized at the time of its submission. This semantic can be encoded in the graph by adding an edge from the future to its continuation. The weakly ordered semantics, on the other hand, indicates that the serialization point of a future is either upon its submission or at its evaluation. To this end, either an edge from the future to its continuation or an edge from the continuation to the future is added to the graph. Either the first or the second edge holds. To emphasize, we have to necessarily select one of these two edges. This graph becomes a polygraph that encodes two directed graphs. And we adopt this bypass inspired by the concept of digraphs of Papadimitriou. Up to now, I have talked about the semantics of transactional futures and their formalization. Based on these semantics, our paper also presents novel implementations of the semantic and the efficiency of the proposed abstraction is evaluated. The implementation is based on JVSTM, a versioned software transactional memory library in Java. The system requires programmers to explicitly identify the transactional objects and store them within a data container called VBox, and that stands for version box. The name version box says that it maintains a list of data versions that are tagged with a version number of transactions committed this version. I have extended JVSTM to provide method to request the execution of a method as a transactional feature as well as evaluate their result. Most of the implementation work is about designing an appropriate concurrency control algorithm. For weak semantics, a graph is employed to track the logical dependencies among the subtransactions. I'll discuss two scenarios from the experimental study. First is a synthetic benchmark we use to exert full control over the workload's behavior. It generates a configurable number of reads reported in x-axis to an array of 1 million elements from within each top-level transaction. Additionally, in between two memory accesses, CPU-bound computations are emulated by spinning for a configurable amount of iterations indicated as iter. We plot the throughput using two top-level transactions, each parallelized with 6 futures. Normalized throughput running two top-level transactions alone, without any futures. As such, the theoretical maximum speedup is 16 times. As this is a read-only workload, there is no use to employ any concurrency control mechanism. We could see from the plot the weak-ordered transactional future achieves close to ideal speedup when the transaction is sufficiently long and contains a fair amount of CPU computation. The performance of weak order and non-transactional future implementation are quite close. This indicates that most of the overhead is inherent to the usage of the future. The second scenario, we use the vacation benchmark. It emulates a travel agency and we parallelize its make reservation transaction using futures. Each reservation consists of a fixed number of search operations within a database of flight, hotel, and cars. We divide these search operations among a fixed number of futures and emulate the scenario in which some futures may have to access a remote database by injecting with a 10% probability a delay of 100 milliseconds right after the beginning of a future. The left figure here reports the left figure here reports the speedup of the weak-ordered semantic, strong-ordered semantic, and multiple top-level transactions with respect to using a single top-level transaction. The x-axis denote the total degree of parallelism that is allowed for each of these baselines. That is the number of active futures by the number of concurrent top-level transactions. Let's use an example to see what is the level of parallelism here. Say at 28 threads, JVSTM runs with 28 top-level transactions here reported as red line. And with blue lines, we see that this is with two top-level threads. So that is 14 futures at a time. First, we can see that both weak-ordered and strong-ordered gain speedup with respect to JVSTM. The reason is the high probability of contention between top-level transactions seen in the right plot here. And JVSTM suffers higher abort rate. Moreover, we could see that from the red plot, both weak-ordered semantic and strong-ordered semantic achieved a similar abort rate by reducing the duration of each top-level transaction. However, weak-ordered scales much better. This work has opened several interesting research directions. The first is regarding the semantics formalization. We have employed a graph-based characterization to formalize the semantics of transactional future, using an approach that aligned with the notation and the formalism used in the classic serializability theory. More recently, an alternative formalization for transactional memory consistency criterion were proposed based on the observational refinement approach, which is rooted on the theory of programming languages. And a natural question that arises in the light of these considerations is whether an equivalent formalization of the semantics proposed in our work could be formalized using a similar approach based on the technique of the observational refinement. Another important line of future research that has been opened by this work is related to the definition of standard benchmark for transactional futures. Unfortunately, in fact, existing standard benchmarks for transactional future are not fit to be parallelized using transactional futures. In particular, the key issue that we encountered during our work while adapting existing standard benchmarks for transactional memory system, for example, the STEM benchmark to transactional futures, is that the granularity of transactions in existing benchmarks is too small to benefit from intra-transactional parallelism. In the future, it would be really helpful and useful for the research in this area to have access to benchmarks representative of realistic application domains. An example of a possible highly relevant application domain in which the abstraction of transactional future would find a natural fit is in JavaScript applications that rely on the asynchronous programming model, in which the abstraction of futures, although non-transactional futures, is already widely employed. That concludes my work. Thank you for your time.